Okay, so let's just take a look at some examples of uh, Bezout's identity and how we can find Bezout's coefficients. Okay, so if we have two values, A and B, and they're in Z greater than 0, then what Bezout's identity says is that there are values S and T that are integers, could be negative, such that the following holds. Such that the GCD of A and B can be expressed as S times A plus T times B. Okay, so these values, S and T, those are called Bezout's coefficients. And so in this next worksheet, we're going to be asked to find Bezout's coefficients. And what we were given is an algorithm. There's an algorithm where you can actually go ahead and use the Euclidean GCD algorithm to find, so we're going to use that to find the GCD, and then we're going to work our way backwards. So I'm going to give a simple example of that so that we can see what that looks like. So first of all, if we were going to try to find, let's see, times 5, the GCD of, let's say, 30 and 4, then we could do that by first, and so this is obviously going to be a fairly simple application of the Euclidean GCD algorithm, but we know that we can use that to find the GCD, and we would go through and we would say 30 is equal to some value. It's a certain number of multiples of 4, so it'd be 7 times 4 plus 2. And then we know that algorithm, and this is just a quick one, but we go ahead and move things down so that we then say 4 is equal to a certain number of multiples of 2. So we're moving everything down, 2 plus 0. And we'll keep doing that until we get to this 0, and then we remember, okay, yeah, then the GCD of 30 and 4 is 2. Okay, this is maybe too simple of one. I need to be one further. So maybe we'll, and maybe I'll do both. We'll also play with finding the Bezout's coefficients of something just one layer up from that so we can see how far back it goes. And so I want to do, I'll do something in 30. Well, we'll start with this, and then I'll just go straight into the real examples, and we can see what that looks like. Okay, so the idea behind it is that then we're going to go from that starting point of the remainder. This is the same, so 30 equals 7 times 4 plus 2 is the same as 2 is equal to 30 minus 7 times 4. Okay, and we're going to use this piece here to kind of work our way back up until we get a Z linear combination of the original A and B. Now this one's fun because I actually have it already, which is why I said it's not a great, I need a better example because here's our 30 and 4 from our starting point. And so the values of S and T are, in this case, 1. That's an awful color on here. We're going to get rid of that. I'll just say 1 and the 7. So those are our 1 and 7 become our Bezout's coefficients. So what we're going to see is the first example is a bit longer. So I'm going to step through the first problem so we can see what that looks like when we start to apply it to something a bit bigger. And what we have here is this. So I'll go ahead and we'll start figuring it out. If we're finding the GCD of 326 and 254, we're still going to start with that same approach of 326 is equal to some multiple of 254 plus a remainder. So we can only fit in one, and then we get a remainder of 72. And we remind ourselves these values, the 254 and the 72 are the pieces that we move over, and we get 254 is equal to a certain number of 72, in this case 3, and what the remainder is will be 38. And again, we'll say 72 is equal to something times 38. I can't fit more than one of them, so it's 1 times 38, and the remainder will be 34. 34 and 38 is 72. Again, we'll move the 38 over, so we're moving over these two numbers. 38 is equal to 134 plus, there'll be 4 left over, and 34 is equal to 8 times 4 plus 2. And we can keep going, but now it gets easy. 4 is equal to 2 times 2 plus 0. And what that tells us is this is our winner. We always go back that 1 and we say GCD of 326 and 254 is equal to 2. But what we want to do is be able to use all of that to find so those Bezout's coefficients. So to do that, we have to go backwards. And I'm just going to use a different color and show us that there are two ways that we can hold this information. So this tells us, this line here tells us that 34 is equal to 8 times 4 plus 2, but it also tells us that 2 is equal to 34 minus 8 times 4. Okay, this also can tell us that 4 is equal to 38 minus 1 times 34. And this tells us that 34 is equal to 72. See, I'm just moving, I'm always moving this piece over to the other side. Okay, 34 is equal to 72, we're going to move this over, minus 1 times 38. And this one tells us that 38 is equal to 254 minus 3 times 72. And finally, tells us that 72 is equal to 326 minus 1 times 254. And you might say to yourself, well, what does that give us? If we put this all together, what we see is that this is a new version of 4. Here's a new version of 34. Here's a new version of 38. There's a different version of 72. And so now we can literally put the pieces of the puzzle together, right? 2 is equal to 34 minus 8 times 4, which is equal to 34 minus 8 times, and here I want to use a different version of 4, 38 minus 1 times 34. Okay, that's fun. What does that give us? Here we've got another 34 in the mix, right? So that's the same as saying 34 minus 8 times 38 plus 8 times 34, right? Which is the same as saying 9 times 34 minus 8 times 38. Okay, so now we can go ahead and put in a new value, which is that value for 34. So we just work our way back up the tree, and we're going to see that we've got another value, and it is a tedious maybe. So 9 times, and instead of 34, we're going to say, well, 34 is the same as 72 minus 1 times 38, minus 8 times 38. And we can pull that out. That's 9 times 72. And we see we've got a minus 9 and a minus 8. So that becomes minus 17 times 38. And that's good because that's the next one on our list, which is 38 is 254 minus 3 times 72. So this is 9 times 72 minus 17 times 254 minus 3 times 72. I did say it's a little tedious, but we're getting now to a number. Bezout's coefficients are going to hang out with 254, and so it's going to be we want something that looks like S times 254 plus T times 326. So now we've already got the 254 in the mix, and we'll eventually get the other value. So we can go ahead and say, okay, well, that's 9 times 72. I'm going to write it all out. Minus 17 times 254 plus whatever 3 times 17 is 30 plus 21, 51 times 72. So all together I can pull the two 72s together. That's 9 plus 51, 60 times 72 minus 17 times 254. Okay, we're getting there. And then last but not least is this one at the top. And so what this says is 72, this whole thing is 60 times, boy, I forgot it all right, 326 minus 1 times 254 minus 17 times 254. It's all of this is just equal to 2. So 60 times 326 minus 60 254s and 17 254s, so minus 77 times 254. And all of that is equal to 2. And so Bezout's coefficients in this space, go ahead and highlight them, are 60 and minus 77. And you can check, so that gives us, Bezout's coefficients are the 60 and the minus 77, where 60 times 326 minus 77 times 254 equals 2, which is the GCD of 326 and 254. Okay, so that is a very long way to get at those values, and you can check that this is actually equal to 2. You should. That's 19,560 minus 19,558, and that is in fact 2. Check. And that is how you do that.